3, 2, okay, yeah. So we're recording, and if you're not right here with us, then you're seeing the archive of this, and we are talking about poly 7, poly 8, and poly 10. And we're not talking about parrots. Okay, we're talking about polynomials. And just a quick thing on polynomial 7. I had somebody asking me the question on this. Where is it? No, that's not the one. Okay, let me go ahead and share my screen with you guys. Let me go ahead and shrink that down. Okay, so polynomials 8. Let's take a look at polynomials 8. Okay, polynomials 8 has 2 investigations that you're supposed to be working on. And the modeling is really where it's at. So if you can do the modeling, you're really making use of this stuff. Okay. Okay, well then you're going to get a preview of today's work. So here in polynomials 8, they start us out with something we should be pretty familiar with by now. They start us out with a third degree polynomial, also known as a cubic. Okay, it says fill in the blanks, use your answers to graph f. The degree of this is an even or odd. This is an even or an odd. Very good. Based on the degree, it's a third degree, so we would call it odd. And the leading coefficient is positive. Therefore, end behavior looks like what? Yeah, leading coefficient is 1. It's positive. So we're going to have this thing yeah, it doesn't have to be exact. You're basically just going to take the zeros, take the y-intercept, take the end behavior, and get it to look, yeah. Left side falls, right side rises. I like the way Carter says that. So falls on the left, rises on the right, and you don't have to like plot like 50 points to make sure that you have the curve just so. You're basically going to look and see, well, what is my y-intercept? What is my y-intercept? I'm actually asking. I'm not asking myself. Very good. Okay, thank you guys. If we throw a 0 in, the x-axis is 0. So if we throw a 0 in for the x's, the first 3 terms disappear, poof, and all we're left with is -10. So we know that this thing will hit the y at 10, -10, when we plug a 0 in for x. Okay, so with that, we a little bit, and they tell us, hey, by the way, an x-intercept is at x equals 1. So what do we do with this information of an x-intercept? And I saw Justin come on camera and talk just a little bit, so don't be afraid to actually use your voice. But yeah, Carter's got us just typing long division. Okay, we take that x-intercept and we say, well, if I've got a 0 of 1, then I have a factor of x minus 1. You take x minus 1, you divide it into, using long division, you divide it into the original cubic, and it's going to spit out a quadratic. If that thing's easy to factor, you're going to factor it. If it's not, you're going to throw it into the quadratic formula. Either way, you should end up with your 3 zeros. Okay? Then it says complete the graph f above, okay, using that information. Over which intervals is f positive? Okay? And then it says the maximum value for f of x for the interval -6 to -5 is what? Okay. Now, if you have done the long division on this thing, one of the zeros is actually what? -5, right? Okay, in fact, the zero that's farthest to the left is -5. So if the zero farthest to the left is -5, and this thing falls to the left, then from -5 going toward negative, this graph is going to be falling. If it's falling from -5 to -6 as we go to the left, that means its highest value is right there where you're inputting -5. And if -5 is a 0, then what is my value at -5? If -5 is an x-intercept, what is my value for y at -5? Yeah, in fact, so the maximum value for that interval would be what? What would the maximum value for that interval be? Yeah. Okay, now, let's see. If you actually go to Desmos, which there's some question, I guess, I don't know, some parents are wondering, hey, is this Desmos really right? And I think it's a great graphing. If you do the long division and stuff, you're going to be working out the factors. So if I come over here and I put in, what was that? Really? Desmos was funky for you? Let me see if this works. Okay, but to me, I kind of think of it as like, if you had some math work and you were doing long division, I wouldn't expect you not to use a calculator. I would expect you to use a calculator. Okay, and to me, that is really all Desmos is like it's a graphing calculator. Okay. So here, if we see, and we can move out on this, move out, and see what I was talking about here, in that from -5 to -6, we have this thing falling. So here's the interval we're talking about. It's a very small interval here from -5 to -6. If that's the, yeah, the pace didn't quite work. I had to change the exponents when I first put it in, but yeah, it saved some time. I just, over here at the handout, I just highlighted it. I shouldn't have highlighted that period, but I highlighted it and hit Control C, that copied it. And then when I went over to Desmos, I went to the cursor and hit Control V, and then it threw it in, and then I just had to, yeah, some PDF files don't let you do that, but these do, apparently. Okay, so here we can see the zeros. We can see the original 0 they gave us, x equals 1. And then we can see that, hey, this must have been a pretty easy one to factor because we got integers for x-intercepts, -5 and -2. So x plus 2 being a factor, x plus 5 being another factor. And then their question F, just trying to get you to take a look at what's going on with the graph, okay? And what else did they ask you? Complete the graph over which intervals is F positive. So for E, if we look back at our graph, okay, what intervals is it positive? Okay, well, basically it's positive between the intervals of -5 and, okay, and then it's positive for everything after 1, right? Okay, After -5, we have negative values. Between -2 and +1, we have negative values. So that's how you would answer that. Any questions on this one? Okay, moving right along. Now this one gets interesting. As we move down investigation 1, we see that we're building a box. Okay. Could we cover yesterday's? We should have time. We should have time, but I'm going to take a look at this box question first. Okay, so taking a look at this box, they say we're going to take this situation where we have this cardboard and we can cut squares out and we can make a box, and we're going to turn it into a graph, because this box is presenting us with a volume problem, and you find volume by multiplying 3 things, and when we have 3 things being multiplied and we got variables involved, then we are going to end up with a cubic. Okay, so if we take a look at this diagram, which greatly helps us, what is going to be our length in relation to this diagram? Oh, Carter was just waiting. He had it typed. It's like, okay, Mr. Loving, and he just hit enter. He's just right there. So, and he's right. Look at the total length of this piece of cardboard. If we cut out squares, and since they're squares, they got the same size sides, same side lengths. Okay, I know, Big Islanders, man. You guys gotta watch out, man. We're gonna just kick you guys all over the place. Anyway, the 12 inches is having 2 chunks taken out, and those 2 chunks, each one has the length x, because we haven't determined the size of these squares yet. Okay, so I nothing against you people who have to live on Oahu, but every time I fly back to Oahu, I look around and I just feel sorry for all of you. I remember it was probably close to 20 years ago now. I'd only been here a year or so, and it takes a while to get used. I mean, it seriously does take some while to adjust to this place. But once you've adjusted, it's like I went back over. Thank you, Vernon. I went over to Oahu, and I remember being underneath at Pearl Ridge Phase 2. I don't even know if it's called Phase 2 anymore. Maybe it's uptown, downtown. I don't know. But anyway, I was underneath the parking lot at Long's. I was looking for parking. And I remember circling around, and I found a spot right in front of Long's. Believe it, if you can believe that. And so as I was parking, I was looking at the windows. I don't know if it's still like this down there, but all this glass with all the cash registers right there and everybody coming out. And I didn't understand what I was looking at for a second. Then I realized I looked through the windows and I saw people buying things, and I saw all these lines of people, and I did not see one smile. Not a single smile. And the place was packed. And I just looked at all that glass and all those people, not one. And I was just like, you know what? We have a lot of people smiling on the Big Island. Anyway, I'm going to go ahead and we're going to go ahead and end 1. And then we're going to keep talking about this modeling problem because I think it's pretty cool. Okay, part 1 is done. And don't freeze. Okay, let's get rolling with part 2. Okay, we are starting in 3, 2, 1, and welcome to part 2. We're just kind of setting up this modeling program and making sure you guys understand that, you know, the Big Island is the best place in the world to live. Anyway, no, I grew up on Oahu, so I, of course, love Oahu too. But anyway, and we just figured out, Jordan and Carter were both telling us that for the length, we're looking at the expression 12 minus 2x. So then what is going to be my width? And he had that typed and ready to go too. Very good. Oh, and they're trying to compete. Actually, Nicholas is one of the Big Island people too. But yeah, so 8 minus 2x. Yeah, because we got the total width, okay, is 8, and we're chopping pieces out. So does everybody got it with the 12 minus 2x and the 8 minus 2x, where we're getting these expressions from, okay? And then what's the height? What's the height? Yep, bingo. Nailed it again. Yeah, if we're going to cut out these squares that have side lengths of x, and we're going to fold up these tabs, okay, or however we're making this box, yeah, we're going to have to fold up each of these things. It's going to have a height that is equal to how much we is. No, it's well contained actually. Anyway, so we're going to have a height that's equal to x. So if we were going to look at that on Desmos, which that's what I'm going to do, right? I'm going to take a look at Desmos, and I'm going to write out. Let's go ahead and X that out. I'm going to write 12 minus x, and then I'm going to write 8 minus x, because that's what we're doing, right? Oops. That's bad. That's the wrong x. Okay, we're multiplying to find volume. Okay, and then what is the height? X. Okay, so here we have our graph. Okay, and this thing gives us our intercepts. Okay, yeah, it is. Let me roll out on this thing. I did something wrong. Oh! No, I did something wrong. Oh, that's... And Carter catches it. No, Carter catches it. It's supposed to be 2. 2 and 2. There we go. That's more like it. Okay. Still pretty steep, but yeah. Okay. Now... Justin solved it without algebra. Do I get extra credit? I'm giving you a virtual pat on the back, Justin. Did you feel that? Okay. So if we multiply these, okay, you guys are going to get an expression. Now, I'm not even going to multiply it. I'm going to let you guys... I'm going to let you guys figure that out, because you guys know how to do hopefully multiplication of binomials. Okay, Carter's got that out there too. Okay, 4x cubed minus 40x squared plus 96x. That's pretty good. Okay, and it says down here, okay, use the graph to help determine length, width, height would give you the greatest volume. Now, how do we find the greatest volume? What are we looking for? Okay, so if I'm looking at the graph, because they're looking at go ahead and look at the graph here. What am I trying to, how does this graph help me find volume? What do these X's and Y's mean? Okay, the height, what about the height? Okay, very good. My x-axis, okay, if we go back to the handouts 8, my x-axis represents the input, which is how big am I making these squares? Depending on how I cut out these squares, that's going to determine what my length is in terms of x, what my width is in terms of x, and what my height is in terms of x. And then that is going to determine my volume, because I'm multiplying the length, width, and height when I have my, well, if you scroll back up and see the, what was it, 4x cubed plus 40, I can't even remember, 4x cubed minus, let's see, yeah, 4x cubed minus 40x squared plus 96x. That is our, you can, if you scroll up, you can see what Carter put up there. That's our cubic. That's our expression. Okay, so depending on how we cut the squares, that's what kind of volume. Okay. Okay, so that is what's going on when I look at my graph. Here, okay, between 0 and 4, okay, if I don't cut out anything, I'm going to have a volume of 0. That's what the 0, 0 is telling me. If you make your x, if you make your height, if you make your squares you cut out, if you make them 0 length and you have 0 height, then you're going to have 0 volume, right? Make sense? Okay. And if you come all the way over here to 4, if you cut those squares out as 4 by 4s, you also get 0. How does that make sense? Why do you get 0 if you cut your squares 4 by 4? Let's go back to, thank you, Vernon. If we go back to the original handout, we scroll up, okay, here's our diagram, okay. If I cut out my x squares so that they are 4 by 4, yeah, I end up screwing up. Carter's saying 8 minus 8. He's saying, basically, you're gonna you're gonna cut off that whole side, right? The width is only 8 inches. So if you go and cut 4 inches on this square, 4 inches by 4 inches, and 4 inches on this side, then it's going to be 8 minus 4 inches and 8 minus another 4 inches, and you're going to have 0 left. So you're going to, again, end up not having any kind of box. Okay? Does everybody understand why when we look at our graph then, if you cut nothing, you get no volume, and if you cut 4 squares of 4, then you cut too much. Yeah, either way, you're shooting yourself in the foot. You don't get a box. You just get a piece of flat cardboard, either for cutting too much or cutting or not cutting, period. Okay? So then what is the highest, the maximum? Well, if you go up on the graph, you look right here, apparently, if you make these boxes about 1.5 inches by 1.5 inches, you're going to get the biggest value. Okay, 1.57. And then the question after that, which Jordan and Carter are answering, is to get a box that has a volume of 64, you would actually come down to, where is, right here. I think I'm at, let's see, okay, 64. To get a volume of 64, you would be 2, right? Okay. And Jordan. But see, the thing that makes me laugh is Jordan's still a Big Island person, so yeah. Anyway. So yeah, that answers that. Now, my to you guys, and is what is going on? Okay, we understand what's going on if you cut off nothing, and we understand what's going on if you cut off 4. But what's this? What does it mean to cut off 5? What is that? Cut off 5 point. What's that mean? A negative box. Yeah, what is that? Yeah, we have kind of shown how, again, a domain can be impacted by context. Remember quite a few weeks ago, okay, before Christmas break, and even before, maybe even before, was that before? I don't think it was before fall break. But anyway, quite a while back, we said that your domain can be impacted by your context. And in this situation, it needs to be we need to understand that there's the physical box sitting there, and that this cubic expression models this situation for just a certain span of inputs. And then after that, I mean, for instance, like, so if you cut 10 inches off, you cut 20, if you make boxes of 30, somehow we're having a box that has, like, what, infinite volume? Okay? So for our situation, for our framework and what we're dealing with, our context gives bounds to what we're going to use for inputs. Okay, so we'll input, even 0 doesn't really make sense, and 4 doesn't make sense, but at least in reality, it's kind of within the idea of, well, you could just not cut anything and end up with no volume, and you could cut too much and just basically slice the whole side off and not have a box. So that's within the context that we're talking about. But any real making of a box is going to involve cutting more than 0 and cutting less than 4. So if we go back to our handout and start answering some of these questions, we're going to look at when they ask about domain and range, what happens if the height of the box is greater than or equal to 4. Okay, I think that you should be able to answer those questions now. I'm going to go ahead and end this part because I'd just really cry if I went over on this one. I'm going to start another part, and we're going to jump back to 7 to answer some of the questions you guys have about 7. Okay, so part 2 is ending. Okay, let's get rolling on part 3, 2, 1, and starting. Okay. Carter saying, can we go over investigation 3? I was going to leave investigation 3 for you guys, oil consumption in Brazil. Oh, I can see why you're wanting to look at it, though. Okay. I think I'm going to leave 3 for you guys to look at, because this is one that it basically, I think I can help individuals on individual questions, but if we start going over this, I'm going to just kind of give you all the answers. So I kind of don't want to go over 3. Does that make sense? No, don't. This is no place for tears. That is a pretty interesting one. Okay. Yeah, so I'll leave that one to you guys, and we'll get to 7. Okay. Okay, Vernon, specific questions about 7. I can't remember how far down we went on this one. Yeah, that's all you guys had to do is the problem sets. Okay. So up, scrolling up. I think we passed it, this one. No? I remember looking at these. Down one page. This one? Page 4. Okay. Okay, says, well, what happened? Okay. Number 6. Okay, find the domains of the following functions using the two-step method. First, define an equation or inequality whose solution will identify the domain. And second, solve the equation or inequality, thereby arriving at the domain. Note, the first one is completed for you. Write your domains in both set and interval notation. Okay, so if we scroll down through A, they're basically saying, okay, step 1, since the argument of a square root, or fourth or sixth, basically even, must be non-negative, okay, the domain will be the set of all x such that 2x minus 1 is greater than or equal to 0. Okay, mathematically we would write this as dom f is equal to x such that 2x minus 1 is greater than or equal to 0, which is read as the domain of f is the set of all x such that 2x minus 1 is not negative. Okay, step 2, okay, solving this, we get x must be greater than or equal to 1/2. Any question on how why the radical is gone and why they're just focusing on what's inside the radical, and then they're solving the inequality and getting x is greater than or equal to 1/2. Anybody have questions on this so far? Okay, which is easier than what they throw at you down below, but okay. So in B, they do step 1 for you. And basically what they're doing in 1 and 2 is they're reminding you of the two, and we reminded you last time on Tuesday, we looked and said, hey, the things you got to watch out for, you got to watch out for radicals because we don't want negative numbers in there, and you got to watch out for denominators because we can't have anything equal to 0 in the denominator. So but basically what they do in A and B is they remind you of that again, and in A, they take you all the way through to the solution, and in B, they start you out by reminding you that, hey, we've got to make sure that 2 minus x is not equal to 0, okay? So then we solve that, and what do we get? We get x better not equal what? Yeah, x better not equal 2. If x equals 2, we've got a problem. So what's the domain going to be? It can be x such that x does not equal 2. Okay? Now, this one, C, is kind of a pain in the butt. Okay, excuse me for saying so, but okay, step 1, we're basically saying, hey, x squared minus 1 has to be what? Greater than or equal to 0. Thank you, Carter, for finishing my sentence. Okay. The problem we get with this is if we solve it without really thinking about what we're doing, we get some kind of nonsense going on. Let me go to the white. Okay, so it's x squared minus 1. Okay, and we'll go to a whiteboard. Grab my pen. Okay, why is it not working? Okay, and we want x squared minus 1 to be what? non-negative, right? X squared minus 1 greater than or equal to 0. So we're like, this is an easy one, right? X squared greater than or equal to 1, right? So take the square root of x squared greater than or equal to 1, square root of 1. So we get x is greater than or equal to plus or minus 1. Right? Case closed, right? Except, what does x is greater than or equal to plus or minus 1 mean? And what's the plus or minus 1 all about? Well, just remember, when we take the square root of a number, the answer is going to be plus or minus, because you can square 1 and get 1, and you can square negative 1 and get 1. So the answer to the square root of a number is going to be plus or minus the number it takes to get back to that number by squaring it, right? You are supposed, now, in many circumstances, the context of what we're doing means we throw out the negative value. So we don't really care that the square root of 64 is plus or minus 8, because most times when we're looking for a square root, we're just considering the positive number. But we do need to take that into account, and especially here, we need to take that into account, because if we look at this one and we just said, oh, so x needs to be greater than or equal to 1. Okay. X needs to be greater than or equal to 1. Is that, well, that's not really the only things it can be, because we can put other things in there and come out okay. Okay, so in this case, we want to be thinking x needs to be greater than or equal to plus or minus 1. But if we look at that on a graph, and we have 0, and we have 1, and we have negative 1, what does it mean for x to be greater than or equal to plus or minus 1? Right, but if I said, like, for instance, is 0 greater than or equal to plus or minus 1? Yeah, see, Carter's writing it out for it. He's saying, well, x really should be, well, x should be bigger than or equal to 1 and less than or equal to negative 1? Is that what you're saying? So we should make x like this. Okay. I think that's, is that what you're saying, Carter? That graph that I just drew? Okay. Why do we not want it to be anything in between negative 1 and 1? Yeah. anything from 0 to -1, see, anything we throw in there, because we're squaring, it's going to become positive. So we have to make sure that that positive is big enough to overwhelm the -1 and not give us a negative under the radical sign. Because remember, this all started out with the square root of x squared minus 1. So any of the stuff in here, let me choose a different color. Any of the stuff in here that we would input, even if it's a negative value here, it's going to become positive. Positive value here is going to stay positive. These will make positive numbers that are smaller than 1. And when we go to subtract 1 away from anything in here that's been squared, right? Those are fractions. When you square fractions, okay? So you're still going to get something that is smaller than 1 when we subtract. But this right here is different from this right here. And so you have to be, even as you're trying to solve this one, you have to be really kind of looking at it and coming at it, you know, from a different angle than just solving it algebraically. Does that make sense? You have to kind of ask yourself, well, what do I want and what do I not want, and how do I get that? It's a different way to, it's a different way, which is kind of tough, because if you look at these two problems, they basically went about solving them algebraically, and then for the third one, they give you a curveball that it's like, if you solve this algebraically, you're not going to get anywhere. Oh, and you can't see what I'm talking about, so let me go back and, yeah, we got to stop this one anyway. Okay, any more questions? I'm going to end this as part 2 and not start a part 3 unless you guys have questions. Okay. Then I will let you guys go. You guys have a great weekend when it gets here. If you do have questions and you just didn't want to ask because I'm like, oh, everybody doesn't want a part 3, that's okay. Just get to me, email me, send me your screenshots. We'll be good to go. Okay? Thanks so much for showing up. You guys have a great weekend. And next time, the Mina bird story. Remind me about the Mina bird story. Class dismissed.